Hello everyone, my name's Lachlan. I'm going to be taking you through the APhO 2023 Theory Question 2. So just a few things I'd quickly say. I think this is quite a hard question, it's quite technical, and hopefully by going through this as an exercise, you'll be able to develop a much better understanding of, cross products and also just doing some rotational mechanics, and you'll become more familiar and confident with that. So the first thing I'm going to do is show you guys the problem itself. Just in case you don't have access to it, I'm going to show you the Australian delegation paper, so the final Australian version of the paper. So we'll just look through each of the pages now. You can pause and screenshot as you wish. Okay, and before we get started, I'd also like to draw your attention. It's really important that you're familiar with a cross product rule, and I think it's good if you have a right hand rule that you can use to get an intuition for the directions. So the one that I like to use is I just do x cross y equals z, so you just point 1, 2, 3, it doesn't really matter which way you want to do it. One thing I will quickly point out is that we work in a right-handed coordinate system. That's the convention that we use. So if the x and y directions are defined, you must define z, so the cross product of x and y is z. There is one rule that I really want to point out to you on the paper, and that's this one here. It's a triple product rule. So that's where we have a cross b cross c is equal to the dot product between a and c multiplied by b, and the dot product between b and c multiplied by a. And I want you guys to have a really good intuition for that rule, so let's quickly talk about it together. So to better understand this rule, let's just quickly set up a coordinate system. So I'm going to set up x is going this direction, then I'm going to set up y going vertically like this. Now, z must be either going into or out of the page. You can quickly use your cross product rule, and you have that x is this way, y is that way, so therefore z must be coming out of the page. I'm going to try and draw it like this. So this is our z direction. Now let's add some vectors onto this. Let's say that we have got c is in this direction, I'm going to call b in this direction, and a is in this direction. Okay, so let's actually quickly evaluate the left-hand side where we do a cross b cross c. Well, in this case, if we do a cross b and use your right-hand rule, you'll discover that that's actually pointing in the direction of c in this case. So a cross b points in this direction. Now, if you have a look, that is now parallel with c. So that means that if we perform this, our answer is going to be 0. And if we have a look, this actually makes sense with what we've got on the right-hand side here, because we have a dot c is 0, and then we've got b dot c is 0 because they have no common component, and so therefore we're going to have 0 multiplied by b minus 0 multiplied by a, so that's just going to give us 0. So it works in this scenario. Now I'd just like to imagine what will happen if we instead make it so our a, rather than pointing directly in the y direction, actually has some component in the x direction as well. So let's do the left hand side. So a cross b cross c. So we start with a cross b. So in this case, our a cross b, if you go and do the right hand rule for this, you're going to see that you end up with some component which kind of looks like this. So when we take the cross product of this component with c, then if we use our right hand rule here, we're going to have a component coming out towards us in this case. So there will be a component which is in the same direction as b. Now if we have a look, this can make sense, because if we have a look at our equation here, a dot c is no longer 0. So that means that we should end up with some component in the b direction. However, b dot c is still 0, so that means that we won't have any in the a direction. Feel free to go back and have a quick look at that again. I just want you to have an intuition for this triple product rule, because we're going to be using it a fair bit in this problem. Okay, so now we've gone through that, let's start with the problem. So we have part 1a here. We need to express the ball's velocity in terms of capital omega, lowercase omega, r, and capital R. To help us do this, I'm going to draw two diagrams. The first diagram I'm going to draw is if we looked at the table side on. So in this case we've got the z direction coming directly out of the table. This is z. And then I'm just going to call this direction the x direction arbitrarily. So we can't actually see the y direction. In this particular case, the y direction with our current coordinates would have to be going back into the page. But I'm just going to make this a 2D diagram. Then we have our ball, might look like this, and it's rotating around. Let's just say like that. Okay, and so it's got some like little r. Now r is a scalar, but it's some distance there. Big R is, I guess, how far away we are. I won't show it on this diagram because it's not really that clear. For our omega, so our omega is, in this case, if the ball is like rolling around like this, then our omega is like going into the page. So I'm just going to represent that with the cross. that's our omega, and our velocity, in this case, if the ball's rolling this way, would be in this direction here. And so what we want to do is we want to use like a kinematic constraint to relate these two parts together. So how does V depend on omega? I think this is something that a lot of people have hopefully seen before. So in this particular case, we're going to get that V is omega cross ZR. Now let's just double check that our directions are correct. So if we apply cross product, and indeed I get the direction of V illustrated in the diagram. Now I want to draw a second diagram because we've only considered the ball rolling. What we haven't considered is the turntable moving. So if I then draw a bird's eye view, let's imagine we have this turntable turning this way. So if we have our like origin directly in the middle, then in our positive Z direction, so I'm going to call the positive Z direction coming directly out towards us, then we are going to have our capital omega, so capital omega is coming directly out towards us. I'm going to call this direction X, this direction Y. Okay, and if we have our ball, to the center of the ball we have a vector capital R, and it's got some velocity V going that way. Then we're going to have an additional component here because we have the table is rotating in addition to the ball rotating. So if we take the table's rotation into account, then we're going to have to add an extra term. So if we like update our formula, we're going to have the same as before, V equals omega cross Z direction R. But now we're going to have this additional term where we have to take our cross product between our omega and Z and R. Now if we just have a quick look at the direction, since like Z's coming out of the page and R's going out that direction, indeed we find that that gives the velocity V direction illustrated here on the diagram. So that's part 1A. Now what I'd like you to do, just to get a little bit of intuition for how this situation works before we go on, I'd like you to quickly have a look at a video of somebody who's demonstrated this really effectively. So what I'll do is I'll just put the link here and I'll put it in the description of this video. I highly recommend just give it a look so that way you can have good intuition about what's going on in the problem. A key thing to notice is that the ball will actually rotate around in the same direction as the table. So if this ball's going to like do a little bit of a circle, then the circle is going to be going in the same direction as the turn of the table. The other key thing to really notice is that the table actually spins around a lot faster than the ball rolls around. The ball, I think, yeah, it only does a fraction of the rotations compared to the table, and later in the problem you're going to see why. Okay, let's do part A2. So for part A2, they want us to use Newton's second law and a torque equation, and then they want us to find the acceleration of the ball. So to do this, let's start by just writing down, in this case we simply have that the force acting on the ball, the net force, is equal to m, and then rather than writing A, I'm going to write v dot. Okay, Newton's second law, thank you very much. Then we have a similar kind of torque or rotational equivalent, so tau going to be equal to, so in this case it's going to be I, and I'm going to write omega dot. But in this case we know that the torque acting on the ball in this case is just going to be equal to the force acting on the ball, cross product with R, and note that this is going to be in the Z direction because R is like directly up and down going from the center of the ball down to the table. So then we've got our torque there, which is nice. So note that I've kind of incorporated the minus sign by doing F cross R rather than R cross F. Okay, so this is kind of like the first part of this question. Then what we're going to do is we're going to substitute into our answer from the previous part. So I'll just put that up so we've got that for reference. Okay, our next step is we're going to have to differentiate. So to be honest, there's lots of different ways that you can go about solving this from here to find V. The way that I'm going to do it is we're going to differentiate V. So in this case we're going to get, now note that R isn't going to, small r is not going to change over time here, so that term we can just differentiate omega. Then we have that for this part of the problem capital omega is not changing, so this is just a constant. And then if we differentiate R we just get V. Okay, then our next step from here is we're going to make some substitutions. So by combining that force and torque equation we can get the following, and so then I can rearrange that to solve for omega dot. Okay, now I can substitute that into my equation in red, and I'm going to get, and from there let's remember our triple cross product rule, which was A cross B cross C, A dot C B, v dot CA like this. Okay, and we're going to apply that to this scenario here. So that first term, if we have a look, we've got v dot cross z more or less, with the factor of mr squared out the front. So in this particular case, our b dot c is going to equal to 1. So that means that our direction that we're just going to get in this particular case is A. And note, because we have unit vectors for z, that means that we're going to get just a factor of 1. That dot product is going to equal to 1. And then when we do our A dot C for the first term, the A dot C part, these two vectors are orthogonal to each other, so that means we're just going to get 0. So if you like, I'm imagining this bit goes to 0, and this bit's going to equal to 1. So let's write that. I'll start using the other side now. So at the end of all that, I just get v dot. Okay, and now what I'm going to do is bring that term to the other side and factorize it out. Sorry, please note I've made a small error. The formula has a minus sign here. I apologize. That should be a minus, which means that this gets a minus. Okay, and now if we bring this to the other side and factorize it out, we get, and then we can divide both sides by the scalar, and we get. Now the only other thing that I'll just quickly say at this point is that in the problem, they actually give us a factor alpha that we are allowed to consider, and in the problem they define alpha as this term here. So alpha equals. Now I'm just noticing that this part of the denominator here looks pretty similar. In fact, let's just rearrange that slightly. If we have a look, that we can just make that so it's all on the fraction over I, and then we get I plus mr squared. So if we have a look, this is actually like the inverse of alpha, but it's on the denominator of a fraction. So what that means is that we can just write this is v equals alpha omega z cross v. Okay, that's part A2. And before we move on to part A3, I just want to point out, if you have a look here, you see that v dot is actually at right angles to v. So that means that our acceleration is at right angles to our velocity. So when this happens, this means that we normally get circular motion. So let's just keep that in mind as we're looking through the later parts of the problem. Okay, so for part A3, what we need to do is we need to find the velocity. And so we've already found the acceleration, so I guess what we just need to do here is integrate with respect to time. So if we integrate both sides, we're going to get the following. Note, alpha and omega are constants with time, as is the z direction. Okay, and when we integrate our acceleration, we're going to get the velocity, and we're going to evaluate this at 2 points. So we're going to do what the velocity is at the current point in time minus the initial velocity. So this bit essentially just becomes v at the current time, and this bit becomes r of t. So then when we substitute in for the 2 times, we're just going to get v, which depends on time, minus v naught. Okay, so then I guess we're kind of done already, but it's kind of convenient if we rearrange this in 2 ways. So the first way I'm going to rearrange it is I'm just going to bring v naught to the other side. Then I'll also write an additional line of working where I absorb v into the brackets with r, and that'll be helpful for us later. Apologies, I missed my cross products, so I'm just putting them back in now. Now, it would have been really nice if I could actually kind of get, factor out this, this z cross, and the only way I can do it is if I kind of think about the triple product in reverse. Okay, and I'd like to get something pointing in my v naught direction. So what I can do is I can kind of just take this expression here, and then if I use my triple vector product trick, then I can see here that where I do b dot c, I'm going to get nothing. But if I do my a dot c term, that's going to be pointing in the direction of v. And z dot z hat in this case is just going to be 1. So in this case, I have this nice property where this is going to give me, in this case, v naught like this. So this means I can actually rewrite this by kind of factoring out my z cross. So I'm going to get that v is equal to this expression here. Now, it's going to be convenient for us in a minute to think about where the center that this is occurring around. What is the origin of this? And it's really handy to do that if you have something that takes the form of r minus. So what we want to do is we actually want to turn this second plus into a minus here as well. So to do that, we can just reverse the order of the v naught cross z. If we do that, then that means that we will now be like this here. So that's our part A3 done. Now A4 is where we really get to kind of think about this, so let's dive into that. Alright guys, so in A4 they want us to find a solution for the ball, the trajectory of the ball. So as we kind of discussed before, we know this is going to be a circle because we had the acceleration was at right angles to velocity, and from this equation here we can actually see that velocity is also at right angles to position. But now what we want to do is actually just get the coordinates of that trajectory. Now I'm just going to do this in Cartesian coordinates. You can do it in other coordinates if you'd like to. Let's just get started. So what I'm going to do is I'm going to break this into like x and y coordinates here. So let me just put my vector symbols back on. And I'm going to call, rather than calling it v, I'm just going to call it r dot. So I'm just going to treat this like it's a differential equation. So if I do this for the x coordinate, so because I'm taking a cross product here with respect to z, that means that my x is going to become minus y. So this means that I'm now getting the minus y component here, and then it's going to be the same for my r naught. I'm going to get the negative y component. Now for velocity, I've done this fancy trick where I've got this z cross v naught, but I could have actually just unfactored this whole thing and just had v naught. So in this case it's still going to be the x component. So okay, then we can also write down a differential equation for the motion in the y direction. When we take our cross product here, we're not going to pick up the negative sign. When you do z cross x, you don't pick up a negative factor. So okay, so this is a differential equation. Now for the moment what I want to do is I'm just going to consider a fair chunk of this constant. So all of this is just going to be some constant. I'm just going to call it d1. And all of this is just going to be some constant. I'm going to call it d2. Okay, and what I'm going to do is I'm going to start by solving the homogeneous equation. So that's where I ignore the constants. And in this case I can see that in this case if I make a substitution, so if, for example, if I was to take the derivative of the first equation and substitute in the second equation, then I would be getting that this equation here, and I can do the same thing for y as well. Okay, and this is hopefully one that everybody's seen before. The double derivative gives you some constant multiplied by a negative version of the function. So this, of course, this is going to be a sinusoidal function. Now you might be familiar with when you are in this scenario that you just take like a constant multiplied by sine theta plus a constant multiplied by cos theta. If you do that in this scenario, it so happens that things are going to be a lot more difficult for you than if you pick a different form. So we can actually just pick the form that Rx is going to be equal to, so it's going to be some constant. So in this case, it's going to be the radius of the circle. So I'm going to call it RT, and then we're going to call it cos alpha omega t plus phi. Now the reason why it's good to choose this is that it takes advantage of the fact that we already know that this is a circular motion. It's going to have a radius of RT, and what we don't know here is some phase factor phi, which is where you actually start on your circle. And then we can use this to also find y. So to do this, what we just need to do to find our y is we just need to integrate up. So we can just use this first equation. We're going to ignore the d1 part for the moment. We're going to deal with the constants in a minute. It's equal to alpha omega and then the integral of rx dt. Note, I'm actually using the second equation here. So I've integrated up the left-hand side where I had r dot y, and I've integrated up this side here where I've got alpha omega rx. Okay, then we can substitute in for rx, and then when we integrate, we're going to get, and this term just becomes 1. And what we also need to consider are there actually are some constants on the end here that I don't know yet, so I'm going to call this one plus c1. Sorry, I just realized I missed a factor of rt on our equation for ry. Okay, so we've got 4 variables to solve for here. We've got rt, the radius of the circle. We've got the phi term, which is giving us our initial phase. Then we've also got the c1 term, which is essentially giving us this initial rx, and our c2 term, which is giving us our initial ry. So let's go through and solve all of these. The best way to do it is we can find what was the velocity at times equals 0 in the x and y direction, and what is the position at time equals 0 in the x and y directions. That'll give us 4 equations that can allow us to solve for our 4 unknowns. So let's start with the initial position. We know that it's given by. Okay, and then we can do the initial position in the y-coordinate. Okay, now we can do the initial velocity in the x direction. So And initial velocity in the y direction gives us... Okay, so what I'm going to do here is I'd like to start with, I'm going to try solving for my velocity terms to be able to get the phi and the RT. So the easy way to get RT that I can see here is that I can actually just take these two equations here, I can square both sides of them and then add them together, and that's going to get rid of my sine theta and cos theta, because sine squared phi plus cos squared phi is going to be equal to 1. So in that case, I'm going to get the following. Okay, and now I just want to solve this for RT, and make a note here that v0 x squared plus v0 y squared, that's actually just the magnitude of v0, so I'm going to express it like that. Alright, and we've just found the radius of our circle, which is great. Now, to find phi, that's going to give us our initial, position in the circle. So what's our phase factor in this case? And so in order to find this, there's actually two ways we can do it, and they're going to be equivalent. I'm actually going to do it both ways because it's going to be a useful substitution for us later in the problem. So I got this equation just by substituting back into my original equation for y. I just divide both sides by alpha omega RT, and I get cos of theta equals this. Now, it so happens that another useful form of it is actually going to be where I keep RT up the other side. So I'm going to write this one here. From that, just solve the following. Okay, and I can also do a similar thing with x. It's going to give us an equivalent answer, so I won't actually solve for phi again. But what I will do is I'll just write it out so we can use the substitution. Okay guys, just to make space, I've shrunk that down. So now we can go ahead and we can find the constants C1 and C2 for Rx and Ry. So to do this, let's start with this equation here. And then what I'm going to do is I'm just going to make our substitution. So rather than writing RT, I'll just write in our expression. And from this, we can get that C1 is going to just be R0x minus V0y over alpha omega. Now, where did I get this from? I used this little trick up here. Okay, and now we can do the same for y. Okay, and so now we have C1 and C2. So finally, we can write out our equations in full. Okay, and we've written up the full trajectory there. Now, just a few key things to kind of note. RT, or the radius of the circle, is the magnitude of V0 over alpha omega, and if we wanted to, we could also find the center of the circle. So the argument I'm going to make for this is that if we have a look at our RT cos theta, RT sine theta terms, this is clearly like the component that refers to just like moving around and around cyclically, so around a center. So the remaining parts, the R0 x and the minus V0 y over alpha omega and the y component equivalents, they actually give us the center of the circle. Now, what I'd like to do is, if we just have a look at those two parts, the x-coordinate of the center is given by this, and what we can do is we can actually just kind of factorize that to get back into a vector form. So if we're asking where is the center of this circle, well, if we have a look, we essentially can just see that one of the components here, this just corresponds to R0 vector itself, and then we have our velocity term. Now with the velocity term, we can't just write this straight away, because if you have a look, we've got the y term paired up with the x term here, and the x term of velocity paired up with the y term of position. So what we can do though is if we take the cross product between z and v, then this will give us the correct coordinates that we want. So what we actually just have to do here is add that term there. And so now we also have an equation for the position of the center of that circle. So that's part A4. Now we get to do A5. Okay, so now we're going to do part A5, and for this bit here, what we want to do is we want to figure out how long does it take the ball to return to the same spot on the turntable. Now note, this isn't the same spot from the labs frame point of view, this is the same spot from the turntable's point of view. So if we just quickly draw a diagram to explain this one, then if we imagine this is like our turntable, and then let's suppose that our ball is doing a little bit of like a circle around like this. There's one extra factor that we just need to consider here, and that's if this is like the center of the table here, distance to there, so that's essentially if that was our initial position, R0, then that needs to have the same magnitude as the center of the circle, RT. And if we have the turntable going around this way, we also have the ball going around this way. And what will happen is the ball will be doing like revolutions going around. That has a frequency or an angular frequency of omega. And then the turntable will be doing revolutions that have a frequency of capital omega. Now, if the ball just does a revolution on the spot, or if it does one complete revolution, then that doesn't actually guarantee that it'll be the same spot as on the turntable. Even though it'll be in the same position relative to the lab, it won't necessarily be the same position with respect to the turntable. So what we actually need is we need these two to essentially line up together. So in order to do that, I guess we need to figure out how are these two periods related to one another. So to do that, from our previous equation, we actually got the angular frequency of the ball's omega. So how quickly it's going around in its circles is given by, we had alpha capital omega. Then we can just substitute in for alpha, and we actually have been given the value for the moment of inertia, I. And so if we do this, what we can get is, nice, so little omega is equal to 2/7 of the big omega. So what that means is for every 7 rotations that the turntable does, the ball should do 2 rotations. What that means is if we just do 7 rotations of the big table, we'll actually know that the ball has done 2 small rotations of its cycle. That actually guarantees that it will be back at the same position in the lab frame, but also exactly the same position on the turntable because they've both returned to their initial positions. So what that means is we just need 7 complete turns, and so the time for that is just going to be 7 multiplied by 2 pi, because that's the number of radians for a full rotation. And we just divide that by the angular frequency, because the faster you're moving, the less time it'll take to do that. And so we get 14 pi over omega is the time to return. Okay, but it so happens there is a special case where we can actually get a different amount of time for the ball to get to the same place on the turntable. The key thing is it doesn't also have to be the same position in the lab. So if we do this, I need to redraw my diagram. Now imagine the ball started in a position like this one here. Then what we could actually have is that this ball could move around this small angle here. In the meantime, the table can actually do a full rotation around like that here. And it's possible that these 2 points could join up again. Now, a key thing that we just need to consider here is that we actually know that this distance here is going to be the same as that distance in there. So we can call that RT, and that's actually going to be the same as this radius in here. And so the time that it takes the table to do this larger angle around the outside could actually be the same amount of time it takes the ball to do this smaller angle here on the inside. So the key part of this diagram that I think that we need to look at is we actually just need to consider the triangles here. So if you like, we're going from some position to another position. So I can draw a straight line going across like that. And then I can actually just kind of divide this into a triangle here that looks like this, and we can divide that one into a triangle that looks like this here. So if I draw those 2 triangles slightly larger, now the key thing is that we actually have to have the distance traveled horizontally in these 2 triangles is the same for to end up in the same position. So this is going to be RT, this is going to be RT, and this horizontal distance here, I guess this is the horizontal distance traveled by the table. So what I'm just going to do is I guess I'm just going to call this X table. It's going to have to equal this distance here, X ball. We're just going to call this angle in here over 2, because that's half the angle that the ball has done if it was going to go around this trajectory here. Now, if we say that there's some angle that the table has done going around, that's actually going to be quite a large angle. And then what we're subtracting off here is essentially 2 pi minus that angle. So what that means is that this little angle in here is going to be 2 pi minus our little angle all divided by 2. Now keep in mind phi here is actually a big angle. It's going all the way around this outside bit here. Theta is a much smaller angle. It's the angle that you do going around this little bit here. Okay, and because these 2 lengths actually have to be the same, and we have our RTs are essentially the same here, we can write down a nice relationship. Just one thing I'll point out is that this triangle only makes up half the horizontal distance. I'm just going to draw in green here. Going from here to there, that's only half that distance. So if we multiply that by 2, then we're going to have 2 multiplied by x of the ball is equal to 2 multiplied by x of the table. Now we can use our angle here. So if we have a look at this x ball here, that's just going to be RT multiplied by the sine of theta over 2. And that's going to be equal to 2 multiplied by RT sine minus phi over 2. All right, and we can do some cancelling. This cancels with that. And then what's inside those brackets must actually be the same. So theta over 2 equals 2 pi minus phi over 2. Those 2's are going to cancel for us, which is nice. Now, we just need to be able to relate theta to phi. But we can do that because we know that the ratio of the angular velocities for how they're moving. From our previous part, we already know that our omega is equal to 2 over 7 capital omega. And so theta, that like angle that's been traveled, that's just going to be equal to omega t, small omega t. That's going to be equal to 2 pi minus capital omega t. And now we can solve for this in terms of capital omega. So first I'm going to substitute in for small omega, and therefore t equals 14 pi over 9 capital omega. And so what we found is that the amount of time it takes is significantly smaller if you just so happen to arrive via this coincidence.